Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. In the last couple of lectures, I went through electrophilic reaction of benzene ring, and I showed you how to replace hydrogen atom on benzene with different substituents like NO2, SO3, halide, or for example, OH. And but like if you want to go further and put a bit more complicated, like substituent, you will see some limitation. And one of them is amino group. The reason for it, nitrogen that attached to two hydrogens and let's say attached to the ring, that nitrogen, it has a lone pair. And because it has a lone pair, it's going to react with any electrophile that is coming actually to the ring. And so nitrogen will be the one that is going to share electron with the electrophile, not the ring. And in that case, we can actually bypass it, or like we can generate NH2 through two reactions. First step, I'm going to put NO2 on the ring, and that's not hard to do. Just simply treat benzene ring with nitric acid and sulfuric acid. Now that we have NO2, we can reduce this one. So next step, we will have reduction process. And that reduction process is going to take NO2, it will turn it to NH2. Okay, so now, okay, I managed to replace technically a hydrogen on the benzene ring by NH2, and like in NH2 does have a lone pair, and so this is one way to do it. Okay, yes, it's not one-step reaction. We had to go and do it in two steps, but we got the product that we are looking for it. And sometimes you will see it as an actual combination. When I say combination, they just simply write, the reagent, and they say 1, 2, 3. And so in this case, they say treat the compound with nitric acid and sulfuric acid. The first step, you will get NO2. Now, if you treat it with the iron or zinc in the presence of HCl, and later treat it with sodium hydroxide, nitro, it will be reduced and it will turn to NH2. Okay, so they listed all the chemical compounds, and they are just simply saying, give me the final product. Okay, now, one issue with the Friedel-Crafts alkylation reaction is the rearrangement. If you take, for example, alkyl halide, that is a primary alkyl halide, and that primary alkyl halide is going to react with Lewis acid like aluminum chloride, and it will generate a carbocation, and that carbocation is a primary carbocation. Okay, we can say if we generate a positive charge on that carbon, it will be primary. Now, primary, we know primary is not stable. So primary is not, we're not going to be able actually to get the primary. Okay, so what will happen? In that case, hydrogen is going to migrate, and it will shift to that carbon, and we will have 1 and 2 hydride shift. And if that one happen, and instead of primary carbocation, we will get a secondary carbocation. Okay, now your carbon is a secondary carbocation, and that carbon is an electrophile. It can attack the ring, and if that one happen, you will get this product. So I have a carbon, a secondary carbon. I need to have 2 carbon attached to it. And remember, 1, 2, 3, 4 carbons total we have. So we can say this is the first carbon, 2, 3, and that's the 4th one. Okay. And so as you see, I got a secondary butyl attached to the ring instead of just butyl technically. Okay, so instead of butyl, I got a secondary butyl product. This is gonna be the major one, and that one it will be minor one. Okay, but the question is, what if I want this product instead of, say, for example, this one? And in that case, I'm gonna say this method does come with limitation, and so the side product will be the major product. So maybe you should switch to different method instead of just simply using primary alkyl halide. Okay. And what's the solution for it? You can use acylation, okay? And I will talk about that one in the next couple of slides. Okay. So I'm gonna highlight some of the limitation with the Friedel-Crafts and the alkylation. The first one, we said if we use primary, it will go through rearrangement. Okay, so instead of primary carbocation, we might get secondary or tertiary carbocation. Okay, and other limitations, if you are using alkyl halide, that halide is sitting on a carbon with the sp2 hybridization, reaction is not going to happen. So in this case, I'm going to say no reaction. Why? Because breaking carbon halide bond, when carbon it has sp2 hybridization, that's going to require a huge amount of energy. So the activation energy is going to be huge, and the reaction will not happen. How about putting the halide on an aromatic ring? In that case, I'm going to say that carbon also has sp2 hybridization. Again, this reaction is not going to happen, so we say no reaction. Okay. So how about this? If you want to have a Friedel-Crafts alkylation reaction, the halide must be on a carbon that has sp3 hybridization. So wherever the halide is, that carbon must have sp3 hybridization. Next thing is, when you put the first alkyl halide, when you put the first alkyl group on the benzene ring, now it will be activated. Why? Because the alkyl groups are electron donating. So if you put the first alkyl on the ring, now that ring is technically, we can say, got enriched up, and electron, now that it has more electron, it will be more capable of running another alkylation reaction. So my point is this: you cannot stop the reaction here. A reaction might go and do another alkylation reaction, and you might get this. You might get two tertiary butyl attached to the ring, and you cannot stop it. You cannot stop it just here. And this is going to be maybe your major product. So that's going to be another limitation for alkylation reaction. And next one is, in order to do Friedel-Crafts alkylation, your ring should not have any electron withdrawing group. And ring must be enriched with some electron, or must have some enough electron density to technically attack the electrophile. And so group like nitrogen NO2, they are electron withdrawing groups, so this is going to happen. They will pull the electron density to themselves. So we will have positive charge inside the ring, and nitrogen NO2, it will have a negative charge. So now what happened? We pulled the electron density of the ring, and because we pulled it, now the ring is less capable of donating electron to an electrophile. So I'm going to say this reaction is not going to happen. No reaction. Okay, so again, let's review. Okay, when Friedel-Crafts reaction is going to fail. One, whenever the halide is attached to a carbon with sp2 hybridization, anything other than sp3. Anything other than sp3. Next thing is, we said if we have electron withdrawing group, electron withdrawing is going to pull the electron density from the ring. Now it will be empty of electron density, or it cannot donate electron to electrophile, so reaction is not going to happen. And next one is the second one. It says if you run alkylation and you attach one alkyl group to the ring gets more electron density. Now this one, it has more electron density. Where did I get the negative charge? Okay, remember those carbon are sp2 hybridization. Well, any carbon here is sp3 hybridization. So that means the ring always is going to pull electron density from the alkyl group. And now the ring, it has more negative charge. Because it has more negative charge, it can get involved in another alkylation process. Okay, So I said, in order to avoid rearrangement when it comes to Fiedel-Crafts reaction, we can use acylation. And in acylation, we have Lewis acid, and the Lewis acid is going to go after the chloride, and it will give us such a compound. Aluminum chloride, we will take this chloride from the compound. This one will be -1. Next, we will have 1, 2, 3, 1, 2, 3, and that's going to be carbon. Okay, I'm supposed to have a positive charge here, and oxygen supposed to have two lone pair on it. Oxygen is going to try to technically stabilize the carbocation, and it will give us such a compound. No, this one has a positive charge. Okay, and this one, it will be the electrophile, and it can attack the ring. And when this one attacks the ring, we will get such a product. So carbon with a positive charge, it will attach the ring. Now we will have oxygen there. Okay, we have 3 carbons here, 3 carbons. So now I got a carbonyl group attached to the ring. Okay. You might say, I don't want the carbonyl. I just simply want butyl group attached to the ring. So how can I get rid of this carbonyl group? We have a couple of methods, at least 3 different methods to saturate that carbonyl group and technically turn it just to CH2. And so we can run a reduction process and reduce this one. And one of the method, it can be the Clemmensen reduction method. And so you will use mix of zinc with mercury, and you will treat it with HCl and also heat. That's gonna technically raise the carbonyl group, and we will have this. So instead of carbonyl group, now we will have 2 hydrogens there. What will happen to the carbonyl group? Carbonyl group is going to leave the system as H2O. Okay. So from carbonyl group, I turn it to a saturated compound, and now I have just simply butyl group attached to the ring. And this is the way technically to bypass the rearrangement when it comes to Fiedel-Crafts limitation. Okay, and this is going to be the end of this lecture, and thank you very much.